I was talking to Raj, and I actually visited you folks a few weeks ago. This is an IEEE talk, so I have tried to make this as general as possible. And I will basically talk about heterogeneous integration. And I realize that not all of you will be familiar with what heterogeneous integration means or why it is so important. Let me start with a definition, if you will. What heterogeneous integration means today is that if you take different entities, for instance, if you consider a graphics processor has a compute chip, it has got memory chips. If you take all of these and make them separately, and then you test them, and then you put them in a package, and I'll describe what a package is, so that when you bring all of them together, you get something that is better than each of these elements. And this idea of heterogeneous integration, which is you make things differently, bring them together, and then you get something that is better than the sum of its parts, is the driving force behind this. And this is something which has and will have a tremendous influence in the growth of computing. So while Moore's law will continue, this will complement Moore's law in a very big way. And the future is a combination of these. And I hope to communicate both the importance of this and what the science behind it is in a very high level in this talk. And if there are any questions, please stop and ask, because no point in holding back. If there's anything that you don't get or want to know more, please ask. Okay. I have to always put a legal notice. It is part of Intel's requirements. And since I still represent Intel, I thought I'd put this. Okay. So what I thought I would do is offer some context to assembly and packaging and test. What does all of this mean and why is it important? And then I'll talk about heterogeneous integration. Why is there such interest? What is the interest and what is the roadmap? I will talk about the area that I personally work in, which is advanced packaging. And advanced packaging can be considered at the tip of the latest technology developments in this field. And when I was talking to Raj, I thought, since I'm talking to a group of students and I have a few years in the field, I might try and explain how my career helped maneuver help me move through this field. So you can take a look at it and see if, how the point I try to make is that this is a complex field. When you get into fields like this, your career takes different directions. And as long as you have the intrinsic skills as an engineer and the desire to do good, you will do well. So I was hoping through some personal examples, I could illustrate the same, I guess. So let me start at the very, very big picture. And where does packaging fit in Intel, and what is packaging? So let me start at the top. Intel, TSMC, Samsung, Global Foundries are the major companies in the world that produce silicon process technology. And we are almost all of us are at leading nodes of these technologies, because Moore's law guarantees almost, or the focus in Moore's law is to double performance every generation and double area scaling in every generation. So Intel, like other companies, develops processes. Silicon processes, interconnect processes, and these get packaged. We design products that take advantage of Moore's law scaling. So if we get double the number of transistors every generation, we should be able to get high performance double or better sometimes. The strength of Intel also lies in the fact that we are able to manufacture these parts. So not only do we design the process, not only do we design parts, but we actually make them. And silicon is a very fragile entity, so it has to be packaged to be protected. We have to be able to connect all the devices on silicon. And if you think about the fact that a 7 nanometer device has a minimum dimension of 7 nanometers, whereas a motherboard has dimensions in millimeters, we are talking about major changes in dimension and connectivity. We also have to protect the silicon. We also have to make sure that there is no loss of signaling or power delivery. So that's where packaging comes in. In addition to all of this, there is a software piece that we take advantage of. And then you have common architectures which allow you to proliferate generation over generation and ensure continuity. So the point is, Intel, with these 6 elements, co-optimizes process, product, architecture, software, and we package to make sure that these are secure, robust, and we manufacture so that the volumes are supported. And in a physical sense, this picture at the bottom should give you an idea. The picture on the top, on the left, is a 100 millimeter by 100 millimeter device, and something that is close to the tip of a pencil. And everything in between is manufactured and packaged at Intel. So think about packaging as the bridge that ensures silicon connects to systems. And the whole process of how packaging works is relatively complex, but it is quite interesting. A wafer is made in our wafer fabs. It comes into our packaging or assembly factories. What we do is we test on the wafer and find out which of the different pieces of silicon on that wafer are good by just checking for certain basic performance characteristics. Essentially, this is called a sort process. After that, we have a process called die prep. What die prep means is you take silicon is often called die, and prep stands for preparation. So you take this wafer and we may thin it if needed. We singulate it or cut through it to create silicon pieces. After that, Intel has a unique process by which we do what is called KGD, known good die, as in we check these die out at a die level. After that, we take these pieces of silicon and we attach it to a package. The package is often called a substrate. And then we put different things to make sure it works. For instance, we can put a heat spreader, as you see in here, so that when a device runs it, if it runs hot, you can cool it. After assembling all of it, we have to test and make sure that it works. So now we have something called functional test, where you run patterns and make sure that the die is working as advertised. After that, you finish it, as in you take the good parts and you clean them up, polish them, you put logo or ID marks, and then we send it on to our groups that figure out ways to make sure that this works in a motherboard, as in we design it so that it works in a system. This is a high-level perspective of the process. It's an extremely complex process requiring a tremendous amount of work to make everything succeed. But the strength of Intel is that at the end of the day, when we do development, our yields, as in from what goes into what comes out, are 99+%, which means you don't throw away too much. You throw away very little, which means the cost of manufacturing is low. To make this happen, packaging is a pretty multidisciplinary field, and we have to do many, many things. We have to develop the process of assembly. We have to pick the right materials. We have to make sure by modeling and experiment that these parts will reliably perform in the places there. Like if it goes into a laptop, it had better survive all the usage that a laptop has. If it goes in a desktop, it should survive that usage. If it goes into a data center, it has to survive that usage. To do this, we analyze the thermomechanical stresses that different materials put on this and how those stresses will change the behavior of the part. The part we build gets put in a socket in a motherboard. We have to make sure that their sockets are able to accept the part we build in. To do all of the manufacturing, we have automation. We have to make sure that our parts fit in the system. So we have to enable it to fit in a system, which means we design the heat sinks, the cabling, and everything that goes on to make the part succeed. Devices run hot, so we have to design our parts so that we can cool them to the right temperatures. This is both a cost and a technical challenge. We have to deliver power to these small devices, and you have to make sure that when you deliver the power, you deliver it effectively and you don't waste too much of it. We also have to ensure that the signals that leave these parts or these that go between the parts within a package have the right level of integrity, as in they don't have distortion. The physical design of the package is by itself a very complex operation. And then we have to get the packages themselves designed, and we have to make sure that we connect the die right. So to do all of this, we assemble a group of highly talented engineers. They are supported by sophisticated labs and design tools and metrologies to make this successful. And it turns out that packaging engineers are extremely multidisciplinary and are extremely well-versed on different aspects, the electrical, the thermals, the mechanical aspects of design. Let me digress a little bit and describe what has happened in this field over the last few years. And I will, instead of a brief history of time, describe a brief history of packaging. So when I started my career at Intel, it was the 90s. At that time, packages were simply devices to make sure that the silicon was kept safe, and it required minimal connectivity. But in the 1990s, a major change happened. We went from using ceramic materials, which had got copper tungsten, to organic materials, which is polymers, and they used copper. Copper is a better conductor than copper tungsten, and we were able to hence get better performance, as in lower loss. Also, organic packages are made at lower temperatures, so the manufacturing energy costs went down. And then the other thing we did was, in the past, if this is a piece of silicon, connections from the edge to the package were made through wires. These wires are long length interconnects, and they are peripheral. We went from wire bond to organic connections by using solder. And instead of connecting only on the edge, we connected to the area. So we got a major advantage and an increase in the number of interconnects. This helped us transition to a low-cost environment. It was copper-based, and it enhanced performance, gave better signaling by bringing connections close to where they needed to be, improved power delivery, and saved a lot of energy costs. So it was an environmentally friendly direction. This transition itself took a tremendous amount of engineering effort and know-how to make happen. As we moved slowly but surely away from the peripheral interconnects to the area array interconnects, we slowly but surely also got rid of environmentally detrimental materials like lead, and we also got rid of halogens in there. While we were doing this, we had to make sure that when we take delicate silicon, we do not put stress to cause a break in the back end of silicon. So we helped ensure that the increasingly fragile dielectric materials on the die were kept safe. This was another tremendous engineering effort. The design of parts which are environmentally friendly and which are able to relieve the stress is a fairly complex task of thermomechanics. And while we were scaling the interconnect between the silicon and the package, we were also scaling the interconnect between the package and the motherboard. So the pitch of the interconnects between the silicon and package is usually called FLI, or first level interconnect. The pitch of the package to the motherboard is usually called SLI, or second level interconnect. And this plot shows you that we were very systematically reducing this pitch, so we were able to give more and more connections as we moved forward. To do that, there was a lot of science developed in transitioning from using pins to using just contact connections. There was a lot of science developed in reducing the solder interconnect pitches using solder joints. And we had to develop a number of technologies to make this happen. Additionally, in the decade of the 2000s, laptops, handhelds started to become popular. So we had to develop parts that were thinner and smaller. And handling thin silicon is an art by itself. All of these developments happened in that decade. And all of them helped make sure that generation over generation, the customers got better and better compute devices. They were better laptops, better desktops, better servers, better handhelds, better phones. All of these were enabled because packaging technologies kept pace. So this brings me to now, this whole idea, heterogeneous integration, if you read the market press, or you will find is a very interesting topic, a lot of interest in this, but it's not a new idea. In 2005, I had an opportunity to help one of our very senior managers present at a conference in San Francisco called Interpack. In that conference, he made 2 points. The first point he made was Moore's law is one of the most important driving forces behind integration. If you can build something on the same piece of silicon, it is absolutely ideal to do it on silicon because you get scaling. If you look at the scaling that is available, or the amount of performance you get in a piece of silicon, it is tremendous because parts are next to each other. They can take advantage of transistor scaling. So silicon is absolutely ideal when you can put this entities or devices you design on the same platform. But if they are built separately, because they can be built and optimized separately, then packaging is ideal for heterogeneous integration. So the word heterogeneous here really means something that is built on a different silicon process and needs to be integrated. Over the years, as people have developed heterogeneous integration devices, we have realized that we need a roadmap that tells the academia, the industry, the research entities, the government funding sources, how is all of this going to be pulled together? So IEEE, in collaboration with SEMI, which is an industry organization, and with the American Society of Mechanical Engineers, together decided to come up with a roadmap. This roadmap says, here are the different things you should worry about, and here is how they will change in the future. So we should get ready for it. This roadmap is today available for download, and it is 562 pages. So it shows you a diverse amount of content, and it helps bring together a broad group of people to drive success. And this roadmap is by itself very diverse. For instance, we look at heterogeneous integration for high performance computing and data centers. We look at it for mobile devices. This includes handhelds. It includes the devices that you, like laptops, high compute, or tablets. It includes medical devices. It includes devices that are related to health and wearables. It includes automotive devices. Most of the dashboard kind of devices or controllers that exist in a car are all included and require a tremendous amount of heterogeneous integration. It includes IoT and sensors, aerospace and defense, where the application requires you to have a very different performance and different level of reliability. We look at how to integrate these components from the perspective of a single chip, from the perspective of multiple chips. We look at what it takes to deliver data using electronics or photonics or wireless. We look at how to integrate power delivery in all of this and integrated power electronics. There are a number of sensors that are included in typical devices, including MEMS, RF. All of these sensors are made part of this. Additionally, when you have wireless connectivity and you have increasing data bandwidth as a function of generations, you have to focus both on how you communicate and how do you package to ensure analog works. We look at cross-cutting topics like materials, new devices that are coming up in the field. How do you test all of these? How do you make sure that there is a supply chain that delivers to manufacturing needs? How do you make sure these are secure and cannot be physically hacked? How do you make sure they are cooled? And then how do you integrate them? How do you create these so-called system in packages? Do you do 2D interconnects, 3D interconnects, a combination? And then the infrastructure, the design, co-design and simulation tools. And if you look at the overall field and the amount of money that goes into these fields, it is in multiple billions, which means you have to have an entire industry infrastructure that makes sure that devices are manufactured correctly, packaged correctly, are reliable, and can fit in systems that can make use of them. So the heterogeneous integration roadmap that IEEE supports pulls all of this together. And it has a very, very broad scope to make sure that everyone has a common direction to work towards. Let me focus, because FIU has a history in health and medical devices. Let me focus just for a few minutes on this. This is not my area, but I was fortunate enough that Professor Mark Polix made a couple of slides for this talk. For medical health and wearable, devices have to focus on different kind of imaging modalities. There are a number of health monitoring sensors that have to be integrated, and these sensors can be made differently and pulled together. So heterogeneous integration has a big role in all of this. When you implant devices, they operate in a very different environment and their reliability is different. So these devices have to be manufactured in a different manner with more environmentally and human-friendly materials. Their qualification pace is very, very different, and the type of data that you expect to get out of it is quite different. To accomplish this, we use all kinds of substrates: rigid substrates, flexible substrates, ultra-thin substrates, different material classes like silicon, glass, ceramic, different metals, different dispensed materials, and different dielectrics. And the way these devices are integrated is also quite varied. It could include electronic communication, RF communication, optical communication. It could involve the use of microfluids and fluidics in different ways, and it comes in various shapes, sizes, and physical attributes. And the qualification has a very different feel to it than typical qualification for high-performance devices. But the point is that even in this field, the idea of heterogeneously integrated components that are optimized separately plays a role. Let me now transition to interconnects in advanced packages. Interconnects in advanced packages form the apex of packaging research, and a lot of these in different levels are waterfalled into different fields. So you will see, if you look at the literature or the public announcements in the last few years, a number of companies have made a number of announcements in advanced packaging which are very exciting. And by doing this, companies like Intel and TSMC have shown the world that if somebody wants to really heterogeneously integrate, we have a very, very powerful set of tools for them. The US government recognizes the value of this, and the Department of Defense recently awarded Intel a fairly substantial contract to develop capability to develop advanced packaging for federal customers. And the idea was advanced packaging will help the Department of Defense develop technologies, their contractors develop technologies that really, really give high performance. Lynn, maybe this is a good time to stop and ask if there are any questions.
Yeah, actually, I just put a survey question in the chat, and so if you can, like, within the following 2 minutes, please fill out a short answer, and I can show the results.
Thank you. So let me address the question of why is there such interest in heterogeneous integration today. So I'll use the example of a field programmable gate array from Intel. This FPGA is built on 10 nanometers, and it is connected to different devices. So the interest to make this happen requires that there should be a high bandwidth memory accessible to the device so that it can do computation more efficiently, and the power spent in this has to be low. We have transceivers, we have optical devices. They are built on different processes than, say, the FPGA, and they are optimized on different processes. They need to be stitched together. The other thing that happens, which is very important economically, is when you create a new process, the defect density is high. So you reduce the chance of you getting a bad die by reducing the size of the silicon, which means you build in yield resiliency. So when you start with a new process, you take smaller die, and then you need to be able to stitch those die on a package. Also, if you want a part which takes advantage of that process, you have to get it out to market pretty fast. So the time to market is an important factor. So these 4 reasons: the need for yield, resiliency, the need to go to time market, the need to enable high memory bandwidth, and the need to integrate different IP optimized on different processes on a package is what drives the evolution of heterogeneous integration. And bottom line is, packages are really great compact platforms for heterogeneous components. In 2019, Intel showed the world that you could take an RF device and stick it next to an FPGA, or you can take an optical device which converts electrical signals into optical and vice versa, connect them using a standard interface. And Intel showed that if you standardize that interface, you can put pretty much whatever you want in here. And we enable universities to come and bid for and build parts using our FPGAs. Just last month, Intel demonstrated the latest status of this work. We showed that you don't just take one optical device, you can take more than one optical device, and you can create connectivity which is tremendous. You can chipletize, like create different chips and connect them. As a result of this, you can enable FPGAs for data intensive devices which work across from radar and electronic defense all the way to wireless communications. This work was supported by the DARPA MTO office, and this was published in 2 conferences, 2019 at the ERI Summit and 2021 at the COMAC conference. To make this happen, interconnects are a key part of the discussion. So for purposes of this talk, I'll describe interconnects as if they are used to connect chips on a package or packages on packages in the XY plane, I call them 2D interconnects. If they are used to connect through the stack, I call them 3D interconnects. Anybody who has built interconnects knows that there are generally broadly two choices. It's the same idea of building roads. Do you build a few connections but allow things to move on those connections fast? This is called the narrow and fast approach or serial approach. Or do you build multiple lanes and allow things to move slowly, but the aggregate of what moves along is still high and you get high bandwidth? That's called the wide and slow approach or the parallel approach. If you compare the parallel approach to the serial approach, the parallel approach sends signals with less latency. It also sends signals across more efficiently. But the reason why parallel approaches did not take off is because they require very complex packaging, and complex packaging is difficult to get and expensive. So till such time, complex packages were not available, the parallel approach did not quite work. However, in recent days, in fact, in the last few years, there are a number of technologies that allow you to do high bandwidth, low power parallel links, because we are able to build higher and higher densities of die-to-die interconnects. And this is fueling a revolution in the way heterogeneous integration works. So how do you measure density? I'll explain through a simple example. We take a piece of silicon which has got copper bumps on it, and those bumps sit on pads on this package. They then connect to wires. These circles you see here are the pads, and there are wires that connect to the pads. And these come from the edge of the die. For instance, this is a compute die connected to memory. So you can look at the number of wires that escape the edge of the die, and that is what's called linear density. In a package, you have multiple layers, so we normalize this by the die edge as well as the layer count. So that's the linear density. And then the other thing is the area array density, or how many bumps or connections do you get per square millimeter of the die. If you want to increase wiring density, you have to reduce the width of this wire, you have to reduce the space between those wires. And ideally, if this circle went to 0, as in it fell right on top of this, you'd get the maximum wiring density. Similarly, if you want to increase the number of bumps per square millimeter, you can reduce the pitch and you will get that. So now for the 2D interconnects, let's look at the landscape of technologies that are available today and what can be done in the future. If we take a normalized metric, which is half the width of the wire, half the diameter of the pad, and then the space between them, and call it half-line pitch, and then plot different technologies available with half-line pitch. At the bottom right, we have traditional organic packages. These are the state-of-the-art, the best-known technologies out there. They give you somewhere close to 50 wires per millimeter of die edge. Now, if you take the same technologies that are used to print the wire and just make finer and finer wires, you can increase it and get all the way up to 250 wires per millimeter of die. If, on the other hand, you use technologies that use ways of building wires in the back end of silicon, you can create a class of technologies that give you 250 to 500. And if you shrink the wires, which is quite possible, you can even go up to 1,000. Now we have a number of wires that are escaping this die and connecting to a device here. The wires are close to each other, so they will interfere. So you have to focus on not only increasing the density of the wires, but you have to also focus on making sure that there is no signal interference, that the power used to send a signal is low. So you get increased bandwidth, higher power density while you get interconnect density. And this forms a fairly interesting field in which you can work. So in 2D interconnects, there are two broad classes of interconnects. The first one is called the silicon interposer, where what you do is you take two pieces of silicon or many pieces of silicon, and you put them on another piece of silicon where you form connections. And then in cases where you want to send a signal from the top die to the package, you send it through silicon vias. This technology has some advantages because you stick silicon to silicon, the expansion coefficient is matched so that the stress is low. Silicon tends to be flat, so you can get very good alignment. You can scale the pitches. But the problem is this base silicon can only be printed up to a certain size or multiples of that size. And that size is typically 33 millimeters by 25 millimeters. That's called a reticle. More than one reticle will require you to do 2x1s or 2x2s. And as you get, your wafer size is fixed. So the more reticles you get, the more bigger reticles you get fewer out of the wafers. Additionally, when you send a signal from the top to the bottom and go through these through silicon vias, there is a capacitive effect on what happens to the signals, and the assembly adds to it. So another idea which complements this is called EMIB, where what you do is you take a very thin piece of silicon and you put it inside the package, and you only put fine featured interconnects locally. These are localized bridges. You can use them to add as much area as you can. You can use different kinds of bridges depending on your application. This process of embedding the bridge is pretty complex, but once you do it, then everything else is natural, and it tends to be a more flexible and less expensive method. So it gives you flexibility, and this was a technology that Intel has put in production now. We can do all kinds of mix and match and stitching. So the idea of heterogeneous integration is really enabled by this concept. And you're no longer worried about reticle. For this picture here, this die is reticle sized. So you get 2 times the reticle, plus you get many other die. So you're no longer restricted by reticle size. Lynn, this is another place to stop and ask if there are any questions.
Sure. I will put it in chart.
Yeah, since the group is not as large as we thought because of the exam, please feel free to interject if you have any questions at this time or even later.
I think also for the first question, right now I only received 2 responses. Maybe I can show that in the end of the presentation.
Okay. Okay, I'll plan to.
Can I ask a question? This is Swami here.
Oh, absolutely. Hi, Swami.
Hey, Ravi, how are you?
Good.
Let me turn on the video. So the question I have is, when you connect these chiplets to each other, so you're making use of, let's say, AIB, right? So what is the additional real estate taken up by this AIB? So if you compare, let's say, the monolithic kind of an approach with this heterogeneous approach, taking into account the area taken up by that AIB, what is the difference? How much extra area is required?
It's about 1 to 2% more, depending on the link.
Okay.
Yeah, because these are typically almost bump limited. And when we get to low bump pitch, they're roughly bump pitch limited. So at 55 micron pitch, it's a very, very low overhead.
Okay.
It is an overhead, but it's a very minimized overhead, if you will. And that number is rough. I mean, I can get you the exact numbers, but roughly that much. And this was always a concern with people, are you taking up more area? But it turns out that the yield advantages of reducing die size overwhelm the increased area due to that interconnect.
The reason I asked that was I was listening to the presentation from Raja, right? And he was stating a number close to 20%.
It depends on how many of them you put.
Right.
When you say Raja, you mean Raja Swaminathan from AMD.
Right.
Okay. Right. They're not using fine pitch interconnects. That's probably why they are higher.
I see.
They are coarse pitch. They are more in the 110 micron pitch.
I see. Okay. So I understand.
And they are SerDes interfaces. The ones we are talking about are digital parallel kind of interfaces. So they're much, much simpler.
I see. Okay. Fair enough. Thank you.
The next transition I'd like to make is to 3D technology. So 3D is the obvious area array interconnect technology, and Intel announced a technology called Foveros, where we take silicon built on 10 nanometers and we put it face to face on a base die at 22 nanometers using 50 micron pitch. I use this picture to communicate a sense of size. If you look at the thickness of the base Foveros die, it is roughly the thickness of A4 paper. So you can imagine being able to intelligently and systematically handle this. And in the future, as you reduce the pitch of the TSVs, the thickness of that Foveros base style will continue to go down. Being able to handle it is a very interesting manufacturing challenge as well. Intel announced a part called Lakefield, and it is in production today. What Lakefield is a device where you have a compute tile on 10 nanometers sitting on a 22 nanometer base die with a memory, a DRAM memory that is POP attached. POP stands for package on package with peripheral interconnect. This whole thing is less than a millimeter thick, and it's 12 millimeters by 12 millimeters. It packs a punch, and it packs a cost-effective punch. Compute, different kinds of IO, memory localized. It can allow you to do a lot at a local level. And we are in production with a single die at 50 micron pitch. Technology development is focused on doing multiple tiles at reduced pitch. And if I just briefly look at this interconnect here between the top and bottom die, it is enabled using solder. As you can imagine, as we shrink the pitch, the amount of solder available and the gap between the bumps reduces to a point where that solder will cease to be very effective. I said IO per millimeter square is a big deal as you shrink the pitch. So there has to be a point at which when you transition, when you just don't have enough solder to make joints reliably. We think, depending on the design, somewhere in the 20 to 25 micron bump pitch regime, you will run out of steam. You will get different opinions on this, and there will be experiments that show you can get very, very low pitches, but the envelope they provide, number of tiles, manufacturing yield, etc., slowly diminishes. But this is not really a cause to worry. It just says you have to plan a transition to go away from solder-based interconnects to copper-copper kind of interconnects. And a lot of scientific work and manufacturing and demonstrations have already been done. So this is now both an economic and a scaling and integration challenge, but the pitches can be scaled lower and you will get increasing numbers of bumps per millimeter square. In other words, the future is kind of bright. We've developed 2D technologies, we've developed 3D technologies. So the obvious thing to do is to merge the two together. And this is the idea of what is called co-EMIB. In co-EMIB, you have a base tile and you can put multiple top die tiles on it. You can shrink the pitch depending on your technology. So I put in less than 50 microns. Now you take a stack and the top tiles can come from different sources. Then you connect the stacks where needed through EMIB. So you get the advantage of EMIB as well. You can also connect them to companion die, companion stacks like high bandwidth memory. You end up getting a fairly versatile set of tiles / components stitched together on a package. And so you are allowed, great opportunity to partition, great opportunity to stitch things together. Now let me try something and run a video to see if this comes across and show how this thing is actually built in a conceptual sense. You take a wafer which has solder on it. So you attach top die to the bottom die. You then encapsulate the bumps so that you can protect them. And you mold this whole thing so you get robustness. You grind off the mold so you expose the back of the die to be able to do cooling. Now you've created a stack of top tiles. You flip the wafer, you can grind it off. You reveal the through silicon interconnects. You can create pads for connectivity to the package. You put solder on it and reflow the solder so you form bumps. This whole thing can be connected. I show a 4 configuration, bridges where you need them, peripheral chips, and you have a fairly versatile platform for. This video has been shown many times, but it communicates very effectively what we mean by the ability to build different parts. I'm going to switch gears a little bit because Raj had suggested maybe we have a conversation on how engineers, especially those of you who are starting your careers, how you think through. So I thought I'd, through personal example, show a little bit. I graduated out of Lehigh. Actually, first I graduated out of the University of Houston and I studied experimental fracture mechanics. The work I do today has nothing to do with what I did in my graduate school. I studied this idea of how can you understand caustics, which is the concentration of light through edges, to see how cracks grow and when do they fracture. I did both simulations as well as studied experimental fracture. At the end of my master's, I talked to the person whose work I had used and who was a graduate school idol for me. I wrote to him and asked him if I could come to Lehigh University and do a PhD under him. And I was fortunate enough that he said yes. So I started working with Professor Erdogan, who was still considered one of the leading authorities in the field of fracture. And I studied fracture in a very mathematical sense, anisotropic materials using singular integral equations. While doing that, I discovered ways of solving some integrals which had not been solved before. So I was deep into this space. It is a surprise somebody offered me a job. But I was offered a job in 1992 by a person who's now a fairly significant person in Intel's hierarchy. He wrote to me and offered me a job, and I started at Intel on May 18th, 1992. So next month I'll complete 29 years at Intel. When I was made Intel Fellow in 2019, I had kept this note because I had looked for a job for 15 months. And I wrote to him and thanked him for doing it. And he was quite happy. I was quite happy he was around when I found a job. The point is that I was able to pay back a little of the opportunity he gave me. While I was at Intel, we in the 90s introduced photomechanics at Intel. Moray, which was then just an idea, became a mainstream technology. In 1992, the highest part dissipation was 4 watts for the 486 processor. Today, we talk very, very casually about more than 250 watts and cool them very easily. Heat pipe technologies were just an idea in those days. They are today mainstream in laptops. We created a journal which is now in its 22nd year of publication. We had this idea of the silicon bridge, which became EMIB and now is in production with millions of parts shipped already. And we've had many years of success in areas that I had never envisioned when I started my job. And I was inspired by some very good people at Intel. There were people who told me that if you work hard enough, you will become fellow. And I was very lucky to become fellow. And I wrote back to them. The point I make out of all of this is he told, one of our senior managers told me that Intel is a company of engineers. And not just Intel, but any successful company where engineering is done, innovation and good engineering is really the core of everything we do. People oftentimes go into different fields and forget that the science behind engineering is what drives success. And people who stick to it in the field both achieve success as well as satisfaction. So to any of you who are young engineers who are looking to see what your future could be, as long as you figure out ways to focus and be effective and innovate, to me, the horizon is unlimited. So to bring this all back, I hope through this talk I have given a sense that heterogeneous integration is a key enabler of performance. There is huge recognition, and if you look at the amount of interest in this field, it is growing. So people who are interested in taking up a career in packaging, this is the time to be part of the packaging world. There is a tremendous amount of interest because there is a need for parallel high bandwidth interfaces. And as I showed you, we have technologies that take advantage of this. From an Intel perspective, we have these 3 classes of technologies, EMIB, Foveros, and co-EMIB. They give us the architectural capability to scale up and scale out. So to me, packaging is an exciting field. It has always been exciting. I have enjoyed my time. I have made very, very good friends and collaborations across the world now. And for any of you looking to take up a career, not just in semiconductor processing, but in medical wearables, all of this is the place to be. This is the time to be a packaging engineer. Okay, Raj, with that, I'll bring this to an end and take questions.